What is electrodynamics and how does it fit into the general scheme of physics? We have the four great realms of mechanics. The first one is classical mechanics, classical, Newton, quantum mechanics, Schrödinger, Heisenberg, Bohr, and the special theory of relativity, Einstein, and the quantum field theory, Dirac, Pauli, Feynman, Schwinger, and many others. Newtonian mechanics works for the mechanics of everyday life, but when it comes to objects that are moving very fast, moving near with a speed that is near the speed of light, the Newtonian mechanics fails and is replaced by the special theory of relativity introduced by Einstein in 1905. And when the objects are very small, extremely small, in the size of an atom, the Newtonian mechanics also fails and is replaced by the quantum mechanics introduced or had been worked on in the 1920s. But when the objects are both very fast and also very extremely small, we need mechanics that combines relativity and the quantum mechanics and the principles, the quantum principles. And this relativistic quantum mechanics is known as the quantum field theory. It was worked out in the 30s and 40s, but until now it's not completely as satisfactory system or considered as satisfactory system. Mechanics tells us how a system will behave when subjected to a given force. We have four basic forces that are presently known to physics, and they are the strong forces, electromagnetic forces, and the weak forces, and the gravitational forces. And they are listed in the order of decreasing strength. Where is the friction? Where is the normal force that keeps you from falling to the ground? Where is the chemical forces that bind molecules together? Where is the colliding, the force of impact that results from two poles colliding together? The answer to that is that all these forces are electromagnetic forces. It's not at all an exaggeration to say that we live in an electromagnetic world. All the forces that we deal with or interact with in real life are, with the exception of gravity, are electromagnetic in origin. Strong forces which hold the protons and neutrons in the atomic nucleus have extremely short range, so that's why we don't feel them. And despite the fact that they are 100 times more powerful than the electric force. The weak forces, which accounts for a certain type of radioactive decay, are also of short range, and they are far weaker than electromagnetic forces. As for gravity, it's so feeble, only due to the virtue of huge mass concentrations like the sun and the earth that we ever notice it at all. The electrical repulsion between two electrons is 10 to the power 42, as large as that gravitational attraction between them. And if the atoms were held together by the gravitational force instead of the electrical force, one single hydrogen atom would be much larger than the known universe. Not only are electromagnetic forces are dominant in everyday life, but they are also the only ones that are completely understood. The laws of the classical electrodynamics were discovered in bits and pieces by Franklin, Coulomb, Ampere, Faraday, and others. But the person who put it all together and in the consistent form it has today is James Clerk Maxwell. The theory is now 150 years old. In the beginning, electricity and magnetism were dealt with as two separate subjects. One dealt with batteries, currents, glass rods, lightning, and the other dealt with magnet bars, the North Pole, compass needle, until it has been noticed that electric current could deflect a magnetic compass needle. Soon afterwards, Ampere correctly postulated that all magnetic phenomena are due to electric charges in motion. By the time Maxwell and Lorentz put the finishing touches on the theory, electricity and magnetism were intertwined. They are no longer dealt with as separate subjects, but as two aspects of a single subject, which is electromagnetism. Faraday speculated that light is too electrical in nature, and Maxwell provided the justification for this hypothesis, and soon after, optics, which is the study of mirrors, lenses, interference, diffraction, was incorporated into electromagnetism. Let's put it this way. The connection between electricity and light is now established, and we possess an electrical organ, which is the eye. The fundamental problem that a theory of electromagnetism hopes to solve is that I hold up a bunch of charges, like in here, maybe I shake them around, and then I want to know what happens to another bunch of charges over there. The classical solution to this problem is field theory. We say that the space around an electric charge is permeated by magnetic and electric fields. A second charge is then in the presence of this field experiences a force. Then the fields transmits the influence from one charge to the other. They mediate the interaction. When a charge undergoes an acceleration, a portion of the field detaches itself and travels off at the speed of light, and carrying with it energy, momentum, and angular momentum. And this is called electromagnetic radiation. Electric charge. It comes in two varieties. We call them plus and minus, because their effects tend to cancel. The extraordinary fact is that the plus and minus charges occur at exactly the same amounts, that their effects are almost completely neutralized. A potato would explode violently if this cancellation were imperfect by as little as 1 part of the 10 to the power 10. Charge is conserved. It cannot be created or destroyed. So the total charge of the universe is fixed for all time. Charge is quantized. It comes in discrete lumps. There is no such thing as 7.3 or a half charge. It's quantized. It is usually appropriate to ignore the quantization altogether, because for example, water too is made of discrete lumps, the molecules, but when we're dealing with large quantities of water, we can deal with it as a continuous fluid. And this is closer to Maxwell's own view. He knew nothing of protons and electrons.